Okay, welcome. So, really already? Okay, my mouse got stuck. Sorry. So, what we want to do today is, hello? Awesome. So, we want to find the flow through an entire network of nodes and pipes that we have. There's 5 total nodes, node 0, 1, 2, 3, 4. And there's pipes that connect all of them. And node 0 is at an elevation of 30 meters. All of the pipes that connect them have a diameter of 0.1 meters. The relative roughness of each of the pipes is 0.01, and the pressure at node 0 is 200,000 pascals, and every other node has elevation 0, and node 4 has an elevation, or a pressure of 0 pascals. So what we're going to do initially is we're going to import NumPy to our environment, and then we're going to import using, no, not using, oh my goodness. Already, let's see, wow, from, we want to import Newton and root, oh. And so what Newton does is finds a real zero of a complex function, and basically what we're going to do is we're going to have a series of huge equations, and then we're going to use arrays, and we're going to pick things out of our arrays, and using Newton we're going to find the zeros of those specific things. Like we're going to find the pressure of the nodes, the internal pressure of the internal nodes 1, 2, and 3, and find the pressure of nodes, or the head of nodes 0 and 4, and then we have, let's do, can I do SciPy? Here we go. And so this does the same thing. What it does is just a vector function. It finds the roots of our function. So again, another 0 finder. But what we're going to do initially is, after this, we're just going to set up some of our constants. So we're going to say that gravity is equal to 9.81. We're going to say that rho, which is the density of our fluid, water, is 1,000 kilograms per cubic meter. We're going to say that mu, which is the dynamic viscosity of water, which is equal to 0.001. And then we have the diameter of our pipes, which is 0.1 meters. And then we have, we'll do the relative roughness of our pipes, and that's equal to 0.001 as well. So we're going to shift enter these. So what we're going to do now is we need to define the friction factor of the fluid in our system. And we're going to use the Churchill equation. And what that does, nope, wrong tab. The Churchill equation predicts the friction factor of our, I'm really sorry, of our entire network. And so what we're going to do is we're going to define their friction factor, which is dependent on the Reynolds number, which is rho dV over mu. And that's the friction factor is dependent on the Reynolds number and the relative roughness, awesome, caps lock, relative roughness of our pipes. And so what we're going to do is we're going to bring in, I did it again, we're going to bring in our variables A and B. And so we're going to say that A is equal to 2.457 times NumPy of the log of 1 divided by 7, and we want that as a float, not as an integer, because Python will yell at us. But we're going to say that 7 divided by the Reynolds number, that times, or raised to the 0.9 power plus 0.27 times the relative roughness of our pipes, and this quantity is raised to the, 16th power. Let's make sure that we didn't type anything wrong. We did not. And then B, part of the Churchill equation, is 37530 divided by the Reynolds number, rho dV over mu, raised to the 16th power. Good, no typos there. And what we want is to return the friction factor function, or I did it again, friction factor function. And so what we want is 2 times 8 divided by our Reynolds number, rho dV over mu, raised to the 12th power, plus 1 divided by a plus b raised to the 1.5 power time, oh, my bad, I forgot parentheses, that raised to the 1/12. And if we didn't type anything wrong, we should be okay. Unexpected EOF while parsing. What does this mean? Oh, missing parenthesis. Cool. And so basically what we could do here is, now that we have this function set up, it will give us the friction factor for our entire system, and we could just pick two random numbers. So I'll say, let's say the friction factor, if our Reynolds number is, we'll do 100,000, and our relative roughness is 0.01. We'll just, actually, let's do the relative roughness that we have right now. So if we do this, one, it works, it gave us an answer, but our friction factor across the entire system would be 0.00558, a lot of other decimals, but we know that it works now. And so from here, what we can say is that we need to create a function that gives us the change in head in our fluid as we move from one node to the other through a pipe. So if I said, let's go from node 0 to node 1, then the change in head would be node 1 minus node 0, and that's dependent on the flow, length, K value, which is, K values are if we have, fittings in our pipe and we have a 90-degree angle, so there's going to be a different K value for that, or if we have a curve, or if we have just a straight pipe, or anything like that. But the K values are different. But what we want to do is to define a function. We'll call it delta head, d head, dependent on flow, length, K value, diameter, and relative roughness of our pipe. And so let me remove this because it's just throwing me off a little bit. So to do this, we need to find the velocity of the fluid in our pipe, which is going to be the absolute value of our flow divided by numpy pi, because in order to use pi, you have to bring numpy in, times the diameter squared divided by 4. And that is our velocity. It should be okay. Do I have too many parentheses? I do have too many parentheses. Oh, wait, I take that back. Hold on. This is not supposed to be, it's supposed to be this entire quantity is the absolute value, because that way we don't have a negative velocity. We just have a constant, regardless of if it's flowing down or up, we know the velocity of the fluid in the pipe. So from here, we can define our Reynolds number, which is rho dv over mu, or rho vd over mu, however you want to say it. Rho times velocity, which we have now defined, times the diameter of our pipe divided by mu. That's me, not mu. Put some parentheses around this just to make sure everything stays nice and happy. And so now what we want is, from this function, we want to return, we're incorporating a negative sign in here in order to dictate the direction of the flow, because we don't care about the speed of the velocity. The velocity is positive. We're not going backwards or forward or anything, but we want to know if the flow is going left, right, up, down. If it's negative, it's left, we'll say. If it's positive, it's right. We'll just say that. But we want to return the sign of our flow times our K value plus 4 times our friction factor dependent on the Reynolds number and our relative roughness of our pipe. I'm really sorry. I think there's a frog in my throat. Times the length divided by diameter, and this quantity is times our velocity squared divided by 2, and this is divided by the acceleration due to gravity. And so if we do this correctly, we could pick, again, any arbitrary numbers for flow, length, K value, relative roughness, diameter, whatever. So if I said, give me the change in head if we have a flow rate of, we'll say 1, and we have a length of 20 meters in our pipe, and a K value of 1.5, and then we'll keep our diameters the same, 0.1, and our relative roughness 0.201. Or let's do, we'll keep it like that. So let's say, all right, give me an answer. So our change in head from our from node to our to node, or as we move from a from to 2, is negative 44.89 with these conditions. And so we know that this is our change in head, and we'll say, okay, it's negative, it's going left. So let's delete this. We know our function works. Let's delete that. And so now we're going to define the flow in our system using a given, or we're going to define, I'm sorry, I apologize. We're going to define the flow in our system using a given delta head. And so we'll say define flow, and we're going to use actual spelled out delta head because we don't want to use this delta head. And that's dependent on delta head, length, K, diameter, and our relative roughness in our pipe. And so what we can say from here, after we put in a colon so we don't get screamed at, is we'll say that our delta head, the absolute value of our delta head, is equal to numpy absolute value of this delta head. I keep pointing with my fingers. You can't see. I can see myself over here in OBS, and it's awful. I apologize. I did it again. Delta head absolute of our given delta head. There we go. And so with this, let's make sure it agrees with us. Awesome. If we set up our function in a way, because if we do our delta head calculation and we get a number super small, an extremely small number, then our Newton root finder, which will come in soon, but that's why I imported this, which I explained earlier, won't be able to output an answer. It'll just break our code. And so we'll say if our absolute value of our delta head is less than, let's do 8 zeros. Let's do 9 zeros just to be safe. 0.901. Then we want it to tell or return to us after I burp, a value of 0, because otherwise, again, like I said, it'll break our code and we won't be able to do anything. And so from here, what we can say is, now that we have this, if we wanted to make, I don't think it'll let us because we don't have, a colon, yes. Awesome. And so let's say, right, I forgot that's not how that works. Anyways, that's embarrassing. So now what we're going to do is we can make a guess for the flow in our system if we assume a friction factor of, we'll do 0.01. And so we'll say our flow guess, Q is flow, is equal to numpy pi times our diameter squared divided by 4 times the numpy square root of our absolute delta head divided by the quantity, our K value, plus 4 times, this is where we bring in our initial guess. Well, let's assume an initial guess of, actually, let's do 0.02, times length divided by our diameter. This quantity is times 2 times acceleration due to gravity. Awesome. And so now, from here, we need to define a function as our flow goes to 0 dependent on flow Q. And so we can say, let's define our function, flow to 0 dependent on Q. And if this happens, we want it to return our delta head dependent on our flow, length, K value, diameter, and our relative roughness in our pipes, minus our absolute delta head. And then once this happens, we can set up our functions, because this defined flow is still under, or everything under this is still under this defined flow function. And so what we can say is, if we want our resulting flow rate to be equal to the Newton function, which will return, again, the zeros of a complex function that we bring in, which is here. If we bring in a complex function, we can say that our Newton will be we want the Newton or the real roots of our flow to zero function and our Q flow guess. And then we want to return the sign of our now delta head function, which is in our flow. Can you not do this to me, please? This delta head times our resulting flow rate. That's just not that either. Okay, and so if we test this, we could say, all right, we want a flow. Let's say we have a flow of -30 with, or a delta head of -30, I apologize. And then we have a length of pipe, we'll say 8 meters or 5 meters, and a K value of 1.5, and then let's keep our diameter at, what was it, 0.1, and our relative roughness at. And so this, given these cases with this change in head, with this length, K value, diameter, and relative roughness of our pipe, we get a flow rate of 0.121, we'll just round, through a specific pipe in our system. And so now, from here, what we need to do is, after I get rid of this, because now that we know our function works, we need to introduce our pipe array to the system. And so what we can say is that our pipes is equal to our numpy array of, let's make sure I type both of these in right. So the array is going to be organized with, let me put that in here. Our array will be, it'll be our from node to the to node with the length and the K value of the pipe. And so we're going to start at node 0, and we're going to say from node 0 to node 1, we have a length of 1.5, and we have a K value of 1.5. We're going to put a comma so we can get ready to set up our next flow. And so now we go from node 0 to 2. We have a length of 2 meters or 2 whatever. We're just going to assume that we're doing meters right now. And a K value of 2 even. We can set up our next node. And so we can say from node 1 to node 2, we have a flow or a length of 1.5 meters and a K value of 0. We'll put a decimal to that too, just in case it doesn't like that. And if it doesn't, we might have to get rid of it later. And then from node 1, we go to node 3, and that has a length of 1.5 meters and a K value of 0, because let's say it's a straight pipe, so there's no bend or anything like that to cause any issues. And then we go from node 2 to node 4, and that connection has a length of 0.5 and a K value of 0. And then finally, we go from node 3 to node 4, and that connection has a length of 3 with a K value of 2. Let's hit escape here and make sure that everything has a comma. And so before I get into, actually, I'll do it in just a second. Actually, I was going to refer to the indexing that we're going to do, but let's make sure everything is okay here. Awesome. So now what we want to do is set up an array for the elevations of our pipe. And so we'll say that the elevation, the only pipe that is elevated in any way, shape, or form is node 1, or the node that is elevated, I'm sorry. So we'll say that our node 1 has an elevation of 30, and then all other 4 nodes have an elevation of 0. And so the next step is we need to specify which of the nodes in this system are external. And the only 2 that are nodes 0 and 4. And the pressures at those nodes, at node 0 is 200,000 pascals or 2e to the 5. So let's say our external pressure is equal to 5th and 0. And then our external nodes are equal to 0 and 4. Let's make sure that works. Did I shift enter this one? I did just now. So this works. So we're going to take this and we're going to put it up here, because if I don't, my code yells at me. So everything that I do down here that works is going to get moved up. And all the things that are going to get moved up are indexing this array, sorry. So down here, what we're going to do is we're going to say that our from nodes, which is, oh, here we go. This is where it comes in. So I'm not going to have any pretty colors. It should just be plain with green. And so what's going to happen is I'm going to be indexing each of these pipes, or these connections. And so if you see here, we have 6 total connections, and there's only, what, 5 nodes? 5 nodes. And so what I'm going to say is our from nodes are equal to the pipes array, and we're going to say that we don't want anything, because it's, when you're indexing, it goes rows, columns. And so we're going to say we don't want anything from rows, because we don't want this entire row. We only want the first column. And since our from node, it goes from to length k, we need our from node indexed at 0. And that will index, whatever, all of these values 0, 0, 1, 1, 2, 3. There we go. And we want this to be returned to us as an integer. Awesome. And then we're going to do the same thing for our from nodes, which is this column, and our length, which is this column, and our k values, which is this column. I know it gets kind of squirrely because I don't have decimals on them, but we'll say our to nodes is equal to our pipes. Pipes. And we want, again, we don't want anything from rows. We only want columns. So we'll say 1, because it starts at 0. So it's 0, 1, 2, 3. And we want this to be given back to us as an integer. Okay, good. And then we want to index our lengths from our array. And that's already, I should have typed, they all have decimals. Okay, cool. We don't want this one given back to us as an integer, but we do want to index it. Again, no rows, only columns. Column 2, again, 0, 1, 2. And then finally, we want our k values to be given back to us as no rows, column 3. Nope, did it again. Awesome. So what we're going to do is we're going to take all of this and we're going to scoot it up here. Wonderful. So now, the next thing we want to do is explain the number of pipes in our array. And so to do that, I'm going to say we'll do n pipes, our number of pipes is equal to, and we want this before I hit shift, and actually I can't shift enter because it won't give it back to us. But what I'm doing here is I'm telling the environment to give back to me the shape of how many pipes we have based on the number of connections. And so if we count, obviously 1, 2, 3, 4, 5, 6, if I type in pipes, it gives me 6 back because we have 6 total pipes or connections. So we're going to shift enter that, and then we're going to get rid of this, and we're going to get rid of this. And so now what we're going to do is we're going to say, okay, well, what's all of our pipe diameters? And when I do that, I'll say pipe diameter is equal to, we want the number of pipes that we have, which is 6, and we want to say that each of them has a diameter. And the diameter that we set earlier is equal to 0.1. So when I do that, I'm going to say, okay, if I type in pipe D, it returns to me that each 1, 2, 3, 4, 5, 6, all 6 pipes all have a diameter of 0.1, which is good. That's what we want. So we're going to dump this up here. Oh my God, what did I just cut out? Okay, well, we know it works. So what was it? Equal to full times our number of, oops, that's an M diameter. That should be right. Let's copy that just to be sure. Actually, awesome. And so we want to do the same thing with the relative roughness for all of our pipes. So if I say pipe relative roughness, that's our symbol for it, is equal to number of pipes So I can say pipe relative roughness is equal to, again, we should get 0.1 e to the minus 3 or 1 times 10 to the minus 3 or 0.001 for 1, 2, 3, 4, 5, 6 pipes. So that works. So we're going to take that. We're going to move it up. Shift enter. We're going to delete this. And so the next thing we need to do is express the number of nodes we have in the system. And so what happens, or not what happens, but we know that we have 5 total nodes. It's nodes 0, 1, 2, 3, 4, 5. And so when we do that, we're going to tell Python Collaboratory or whatever that we want the maximum number of pipes. I apologize. The maximum number from our system or from our array, and we're going to index our 2 nodes. And when we do that, we want that to be returned to us as an integer. After I learn how to type, that's not even close. And then we want to add 1 to that. And so if I don't do that, I can say, all right, look, it says we have 4 nodes because it doesn't want to let us start at 0. So if I do +1, and then I do this, it gives us 5. That's the total number of nodes that we have. So let's do. So again, let's say that we are indexing pressure, elevation. Nope, not pressure, I apologize. Elevation from 2 nodes, length, K value, number of pipes, number of pipes, and the diameter and relative roughness of each pipe. And we're making sure that the environment knows how we want it to act. And so then what we're going to say is, now that this is up here, let me delete this. We're going to say that we want the number of heads of the fluid in our system to be equal to the zeros, nope, that's not how you spell that, of the number of nodes that we have. And so when I do that, if I type in heads, it will give us all 5 zeros for the number of nodes, which again, when we figured it out, we have 5 total nodes. So we can do that. We can say, okay, goodbye. Hello again. And then the next step is to say that the heads in our system, let's make sure I do this one up here because this is where it sometimes acts up on me. In our system of the external nodes, is equal to the external pressure in our system. In our system, which again we've mentioned up here earlier, divided by rho divided by gravity plus the elevation of our external nodes. And this is giving me an unsupported for type list and float. Maybe if did I add an extra decimal somewhere? Or am I missing one? Sorry, these are just the parameters. ... Okay, that one doesn't need one. Why are you external pressure Let's figure out why you're not working properly. I'm not entirely sure why. These are worthless. Okay, well, that's interesting. What if I did, let's hashtag that, and we can see if we can come back to that later, or when we actually need to deal with it. But this line is supposed to give us the head elevation of the external nodes in the system, and why it's not working is confusing. What if I just, okay, so let's do that the internal nodes of our system is equal to a list from the set in the range of our number of nodes minus the set of our external nodes. Okay, that works out. Okay. That's concerning, but we're going to keep going. So the next step is to define a function that calculates the flow of fluid through our system dependent on the head of each of the pipe in the system. And so what we're going to do is we're going to use the integrated values or the iterated values of the fluid heads in the system. And so we're going to define a function. We're going to call it calculate flows. And we're going to say, again, it's dependent on the heads. And we're going to say that our flows equal numpy zeros of our system for the number of pipes in our system. And let's do flows. Okay, well, I just defined it, but still. Okay, well then, what we're going to do now is we're going to say that for every I that we use, and we're just going to index that in the range for the number of pipes that we have, we're going to say that our delta head is equal to the heads in our system of the two nodes for the I value, excuse me, minus the heads in our system of the from nodes I value. We're going to shift enter that. Okay. And then we're going to say that again in this range that our flows dependent on I are equal to the flow of our delta head, or is dependent on the flow of our delta head lengths, there we go, I, K value I, diameter, nope, sorry, pipe, I, and then our relative roughness, I. Once that's done, we want to return the flows in our system. So now if I say flows, it would return them, but I don't have any numerical values in here. So now that we have the flows of the system returned, what we want to do is calculate the total flows throughout the system, through all of the nodes in the system. And so if we say, okay, let's define the function calculate net flow Q dependent on the flows in the system, we can say that our net flow Q is equal to the zeros of our number of nodes function. Okay, good. Everything is in agreement. And so what we need to do is say that we're adding to our net flow dependent on the indices, and we're going to use our to nodes and our from nodes. And then we're going to say, that's wrong. I don't know why I typed that. It should be flows. And then we're going to do the same thing for our net flow leaving our from nodes. And we're going to do negative flows. Because again, the negative flows indicates any flow leaving a node. And then we're going to return the function, or not return the function, but we're going to return our net flow in the system. Okay. And so now the next step in our environment is to create a function that finds the roots or the zeros of the net flows. And so for this to work, we need the internal, or the flow for all the internal nodes to be 0. And so what we're going to do is we're going to define a function where our net flow internal dependent on our internal pressure. And what we're going to say is that our heads of our internal, can I spell, nodes is equal to the internal pressure divided by rho divided by acceleration due to gravity plus the elevation of our internal nodes in the system. Okay, that agrees with me, but this one decides that it doesn't want to, which is interesting. Okay, so from here, we want it to return to us the calculated net flow, and that's dependent on the function from above of our calc flows. That's dependent on our heads, and then we're going to say that we want this to be indexed at our internal nodes. Okay. And so from here, what we need to do is we need to say, okay, let's take a guess at the internal pressures in any of the nodes of the system. And so we can say, all right, any of in nodes node to 4 or 0 to 4, I'm sorry. So we can say that our internal head guess is equal to the mean or the average of the heads in the system dependent on the external nodes. And I think this might be where we get a bit of an issue because, oh, it didn't work, or it didn't do it. All right, well then. Next, we need to specify an internal pressure guess in our system. And so what we're going to do is, pressure guess in our system. And to do that, we're going to say that we're going to reference our internal head guess. And we're going to subtract the elevation of our internal nodes from this. We're going to multiply this function by our density and our gravity. Internal. See, this is where we pay attention to the things we type. Okay. And so now, what I'm going to do is I'm going to get the result of our internal pressures in all of our nodes from our system. And so if I say, okay, let's get the result of and we're going to find wait for it. Using the root function, we're going to find the root of a vector function flow. And we're going to say, okay, give me the root of the net flow in our system internally, internal, and using the internal pressure guess. I misspelled the words zeros. I wrote it the wrong way. I think that might be the one. I did it again somewhere. Zeros. Zero. Wait. Zeros. 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 Interesting. Let's do it like this then. I'm just checking to make sure I didn't misspell anything anywhere. Hello? Has no attributes zeros, but none of them are flows equals flow. The flows. Define calc flows heads. Define calc flows heads zeros. Haha, there you are. What's the issue now? Pipe D, not defined. That's because it's lowercase. Man, you see? We're making good progress, and it was for nothing. Ladies and gentlemen, the power of troubleshooting. So, if I type result, let's see if we get an answer. So, the pressure of our internal nodes is 0, which shouldn't be that. I think that might have something to do with our messed up heads equation here. External pressure. Do I need a decimal somewhere? Maybe that's what it is. Let's try that. Oh. Nodes pipes, so we're using external pressure divided by, but that is a float, and so is that. External nodes is a list. Okay, well, again, everything besides this has worked up until this point. So what we're going to do is we're just going to get rid of that, and we're going to shift enter that. And so hopefully when that is fixed, we can get an actual result. But we're nearing the end of the calculations, and so, let me remove this. So what we're going to do is we need to calculate the flow of the fluid through each of the pipes in the system. And in order to do this, we need to print each of the flows of the pipes using this initial array that we used earlier. And so what we're going to do is we're going to say that our calculated flows are equal to the calc flows function that we used earlier dependent on the heads. And then we're going to say that for in range, for the number of pipes that we have, we're going to print the from node, and we're going to say, okay, we want int of the pipes, that's a 9, not a parenthesis, pipes, and we want our from node, so we're going to say I0. We're going to close that and close that, and then we're going to say, okay, 2, we're going to do the same thing. We're going to say int pipes 1 pipes. Why am I putting extra parentheses in here? No, I'm not putting extra parentheses in here. I was lying. And then our last one is going to be our flow to each of them. And we're going to say, all right, give us the calculated flows I in the system. And then we're going to close that. And we're going to say, and parentheses. I see, you gotta double check this stuff because we don't want spelling errors. And then we're gonna shift enter. Whoops. Why? Syntax of our function, but I'm not sure why this is the case. Pipes. Oh, we're missing the parenthesis. I was looking at the wrong thing. Ah, yes, you see. Calc. Man, sure it'd be easier if I knew how to type. So again, the issue, I believe, is up here. And that issue is going to become very prevalent down here when we use our pressures, because the final step is to print out the calculated flow, or the pressure for each of the nodes in the system, and the external and internal. And then doing pretty much the same method, but we're going to use that, and we're going to say that our calculated net flow in the system is equal to our calculated, or see, I did it again, calc net q of, that's parentheses, calculated, or calc flows dependent on the heads in the system. Good. Now we can say that pressure is equal to the numpy zeros, let's spell it right this time, of our number of nodes. Okay. Pressure of the external pressure is equal to external P. But does it work for internal? Because that one didn't give me an error. Okay. And then we can say that for, again, doing the same print method, the number of nodes that we have we can say that we want to print the we're going to say that our node number is I, and then we want our pressure, we can say that, oh, actually, no, that makes sense. Pressure is and then we can go and say that our elevation for each of the nodes in the system is Z of I. And finally, we can say that our net flow is our calculated net Q I. And it'll print all of them, but, oh, let me put a space here. So, that being said, our issue is here and here. But I'm not sure why that could be. Because we aren't doing anything different than we've done in the past regarding our codes. And I'm upset because I've gotten values before. Huh. Our external nodes are nodes 0 and 4, but it doesn't like us for this, for putting this stuff in here. And I don't, oh, well, the issue is now this cell is so big that I'm unable to really even crack a guess at why this isn't working for us. Because up until now we've been free and clear. Unsupported operand. Alright, let's see if maybe this will. You want to keep the data as int. But oh. So if I do but all my lists are the same size, I think. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. that is aggravating because I am unsure as to why. Because I know it would work if this would work. For list and float. External nodes 0, 4. External node 0, 4. Oh my god, wait a minute. Our pressure needs to be enclosed. It doesn't need to be enclosed. That's weird. Our pressure is an array. Our pressure is an array. Our pressure is an array. So now, for our 3 internal nodes, let's start here. Our 3 internal nodes, for node 1, we have a pressure of 82,620 pascals. For node 2, we have a pressure of 53,908 pascals. And for node 3, we have an internal pressure of 74,034 pascals. And then from here, what we can do is we can display this and have it print out from node 0 to node 2. Wait, let's make sure these are right. 0. Should be 0 to 1, 0 to 2. Whoa. Nope, that was wrong. Don't do that. Well, from 0 to 1, we'll say. But we have the pressure, elevation, and net flow. Ooh, can I do... Oh. That's irritating. Why can't I? Whatever. We have the pressure, node number, elevation, net flow, and the net flow for all of our nodes. That was a doozy. What we got there?